Welcome back to the deep dive. If you track the history of computer science, or even, philosophy, the fundamental question for centuries was remarkably simple.
Right. It was all about existence.
Exactly. Is this problem solvable at all? Can we theoretically write down an algorithm that eventually, maybe in a billion years, finds an answer?
In our field, we call that the question of decidability.
Hmm.
And for a very long time, simply proving something was decidable, that an algorithm even exists and is guaranteed to halt. That was the victory.
The whole focus was on the possibility of computation.
Hmm.
But the reality of computation in the 21st century is fundamentally different. Computation is embedded in everything we do, from high-frequency stock trading to rerouting global logistics in real time.
So merely being possible is nowhere near good enough.
Not even close. The question shifts entirely. It's no longer, is this problem solvable, but rather, and much more pressingly, how fast can we solve this before the data becomes obsolete or the sun burns out?
We have absolutely transitioned from a philosophical debate about existence to a hard engineering constraint about time. We're living through a massive practicality crisis, where theoretically sound algorithms might take longer than the age of the universe to actually execute.
And that is the core theme of our deep dive today. Our mission is to move squarely into the world of computational complexity theory. We're going to define a formal, rigorous, and crucially, machine-independent standard for what efficient actually means.
We're drawing a line in the sand.
A clear, bright line. And we're going to introduce you to the comfort zone of computer science. The robust class of problems that are truly, as the foundational text suggests, practically feasible within a reasonable lifetime.
And to immediately illustrate why this shift in focus is so critical, we have to start with a classic example that just breaks the theoretical model.
The traveling salesperson problem, TSP.
TSP. The idea is simple. A salesperson needs to visit, say, doll cities exactly once, and then return to their starting city.
And the question we ask is a decision problem. Given a total distance, let's call it Tachaners, is there any route that covers all many cities with a total distance less than or equal to dollars?
It is the absolute poster child for this dilemma. From a theoretical perspective, yes, of course it's decidable. We can write an algorithm for it.
You just check every single possible route.
You systematically check every single permutation. Since the number of cities, none is for finite, the number of possible routes is also finite. The algorithm has to eventually halt.
So technically problem solved, but let's talk about the resources needed for this brute force approach, because this is where theory just smacks right into the wall of physical reality.
The problem requires exponential time in the worst case. The number of paths the algorithm has to check grows roughly as none in factorial. All known exact solutions have this cost function that just balloons exponentially.
Let's ground that exponential growth in a shocking, concrete example for you. We're not talking about a million cities. We're talking about a pretty moderately sized logistical challenge.
Let's take 70 cities. In modern global logistics, 70 destinations. That's nothing.
That's a Tuesday.
Right. Yet, solving the 70-city TSP using the most direct, exhaustive checking methods requires a number of steps that is roughly on the order of 2 to the power of 70.
Okay, so that number, $7, is just abstractly massive. What does that actually translate to in time on a really powerful machine?
And we'll use generous estimates here to make the point even stronger. Imagine you are running this on a modern supercomputer, one capable of executing a blazing 300 billion instructions every single second.
Okay.
You set that machine running today to solve this modest 70-city problem. It would take around about 120 years to return the guaranteed optimal answer.
120 years?
120 years.
The information is completely irrelevant by then. The cities themselves might be gone, the salesperson has definitely retired before the computer spits out the answer.
And that is the core conclusion we have to internalize. If the most robust, guaranteed solution takes 120 years to compute, then the theoretical solvability of the problem is utterly useless.
It's just a footnote.
It's a footnote. And this is exactly where complexity theory steps in. It provides the essential, robust framework we need to differentiate problems that are just possible from those that are practically usable in the real world. We have to define easy and hard based on how these problems consume resources like time and memory.
Okay, let's unpack that and establish our measuring tool. If we want to classify problems as easy or hard universally, and by that I mean the classification holds up whether you're using Python on a laptop, a specialized chip, or some future quantum hardware, we need a foundational standard machine that defines time consistently.
That standard model, as old as the field itself, is the Turing machine, or TM again. Complexity theory, at its heart, studies resources: time, memory, parallelism, even how much randomness an algorithm needs.
But for this basic classification, we're focused on time.
We focus on time and we measure it on the TM.
Okay, but I have to push back on this a little bit. Why are we still talking about theoretical tape heads and infinite tapes in 2025? Isn't that simplification so massive that it makes the results totally irrelevant for a modern multi-core CPU or a GPU?
That's a fair and absolutely critical question. We rely on the TM precisely because it's the most minimal model of computation that still adheres to physical laws.
Minimal in what sense?
Every single action a TM takes, moving the head one spot, reading a symbol, writing a symbol, it costs a measurable, non-negotiable unit of time and energy. By standardizing on the simplest possible machine, we establish a classification that minimizes the influence of any implementation-specific tricks or optimizations.
So you're stripping away the noise.
We're stripping away the noise. And since we're only concerned with decidable problems here, problems we know will halt, our only remaining concern is how long that halting takes.
And when we measure this time, we aren't looking for the best-case scenario, where the data happens to be perfectly aligned. We're looking for an ironclad guarantee.
Absolutely. We rely on worst-case analysis. This is defined by a function we call time m of n. What we do is we fix the length of the input string to some number, 9.
So say 1,000 bits.
1,000 bits. Then we look at every single possible input string of that length, every possible arrangement of those 1,000 bits. We find the single one that forces our Turing machine, M, to take the absolute maximum number of steps before it finally halts.
So you find the most difficult, most time-consuming arrangement of data for a given size, non-dollars, and that maximum time becomes the official runtime for size null-letters.
And this choice is vital because it ensures the complexity depends solely on the size of the problem, which is $, not on some lucky structure or content within the data. We want a classification that allows a programmer to constantly tell a logistics company, if you give me a problem with 1,000 data points, this algorithm will finish in at most this amount of time.
Regardless of what those data points actually contain.
Exactly. It's a guarantee against pathological worst-case inputs.
Let's work through a quick example to see how calculating these worst-case steps forces us to focus on how the problem grows. Let's consider a simple language, $1 and $1.
Right. This is the set of all strings that have some number of zeros, $1, followed immediately by the exact same number of ones. So 00011 or 00001 above.
But not 001. The counts have to match.
The counts have to match perfectly, so we need a TM algorithm to verify that. And it's a fundamentally iterative process because the machine can only look at one tiny part of the tape at a time. It has to compare the stuff on the left with the stuff on the right.
So walk us through the motion, step by step. For a string of length, what, $2 long?
Okay, the machine starts at the leftmost zero. First, it marks that zero. Maybe it changes it to an X to know it's been processed.
Yeah, okay.
Then it has to move its cape head all the way to the right end of the string, skipping over all the other veers and all the ones until it finds the first unmarked one.
And it marks that one too.
Marks that one, say, changing it to a Y. And then phase 3, it has to move its tape head all the way back to the beginning to find the next unmarked state.
So it's like this pendulum swinging back and forth.
It's a pendulum. And the input length is 2 milliliters. For that very first pair comparison, the machine has to travel almost the entire length of the tape out and then back again. If we ignore a few constant steps for state changes, that's about $2 million steps, roughly.
Right, that's the cost for the first pair.
That's the first cycle. Now, it has to repeat this process $, times, once for each pair of 0 and 1. But, and this is the crucial part, each time it repeats, the distance the head has to travel gets slightly shorter.
Because 2 characters have been marked off and are now ignored?
Exactly. 1 niller and 1 len are out of the game. So the steps for the $, cycles look something like this. Cycle 1 is about $2 steps. Cycle 2 is about $2 steps. Cycle 3 is $2 an L, and so on, all the way down until the last cycle takes just a couple of steps. Right. And when you sum up that series, $2 plus 2 and 1 plus 2 and a 2, all the way down to 2, the formula for that total number of steps contains a dominating term. The sum of 1 through $, is roughly $, squared over 2.
So times 2, you get something proportional to $2.
The total steps come out to be something in the order of $2 plus $.
So for this particular problem, the runtime grows quadratically. And that detailed step-by-step arithmetic perfectly demonstrates why counting exact steps is, at the end of the day, pretty pointless.
right? We just went through all that painful arithmetic and found the runtime is proportional to something like $2 plus n dollars. But we could have optimized the machine slightly, maybe added an extra state, or changed how we marked the symbols. That might change the exact formula to, I don't know, $5 plus $10, or maybe $3 plus 100 steps.
And that exactly is why the source material describes this kind of exact step counting as tedious and often pointless. We're just drowning in implementation-dependent noise.
It feels arbitrary. It is. Did the programmer choose to use one extra intermediate symbol on the tape? Did the specific encoding of the input require an extra travel step? These tiny details skew the constant factors and the lower-order terms, but they don't change the fundamental difficulty of the problem.
So the crucial universal information isn't the exact step count, it's the growth rate, the asymptotic behavior.
Absolutely. Does the time grow linearly, quadratically, cubically, or, God forbid, exponentially? That question is machine independent, it's implementation independent, and it's the absolute key to complexity classification.
And to capture that big picture, we rely on the dollar notation big O, which is basically a mathematical shorthand that ignores all that noise and focuses only on the dominant term.
The O notation allows us to categorize functions by their order of growth. We formally say a function fires an in if $5 grows no faster than dollars.
Let's try to make that formal definition a bit more palatable for someone listening. The definition talks about finding constants, $sic and $dollars, such that $5 is always less than or equal to times $8, but only for large inputs. What do those mysterious constants, $6 and $dollars, actually represent for us?
Let's start with NVS. This is the sufficiently large input threshold. The complexity of an algorithm for tiny inputs, say an input of size 10, is often completely irrelevant.
Right, who cares?
Who cares? We only care about how the algorithm behaves when it's truly stressed, when the input size is massive. So Nathlo just says, look, once the input gets big enough, then our classification kicks in and starts to matter.
And what about $10, the constant factor?
$1 is our free pass for hardware and implementation improvements. It means we just ignore constant factors. Your algorithm that takes $5 plus $10 is, from a complexity standpoint, functionally the same as my $3 plus $10 algorithm.
Because that constant difference is negligible in the long run.
It is. And better hardware or a more clever programmer can easily erase a factor of 5 or 10. For complexity theory, we're only worried about the function's overall shape, not its specific height.
So if we go back to our earlier example, the function was something like $5 term equals 3 and 2 plus 5 lies?
That function is in 1 or 2. As goal gets really, really big, that $5 term becomes utterly insignificant next to the 3 intonated term. It's a rounding error, so we just throw it away.
Okay, so the lower order terms are gone.
They're gone. Then we ignore the constant factor, the 3. Why? Because we can always find some other constant, say 244, such that our original function, $3 plus $5, is always going to be smaller than 4 and 2, as long as it's large enough.
The dominating term, the 2n2, that's the true fingerprint of the algorithm's difficulty.
And this rigor is what lets us formally define complexity classes.
Indeed, we use this to define a class called DTIENT. This is the set of all problems, or languages, that can be decided by a deterministic Turing machine in a time that's bounded by the growth rate. So our language from before, $1, is in DTIMELR. It's a quadratically solvable problem.
That's its home.
Now, before we get to the gold standard, you mentioned a technical constraint. The time function $1 has to be realistic. What happens if we just use some bizarre, exotic time function?
We enforce 2 simple constraints. First, Tn has to be at least blending dollars. You have to spend at least a lot of steps just to read the input of length dollars. No useful algorithm can possibly run faster than linear time.
Makes sense. You have to look at the data.
You have to look at the data. Second, Tn must be what we call time constructible.
What on earth does it mean for a function to be time constructible?
It's a bit of a technicality, but it basically means that if we're going to define a class based on some runtime limit, there has to actually exist a Turing machine that can halt after exactly Tn steps. It's a stopwatch. This just prevents us from using abstract, uncomputable time functions to define our classes, which would defeat the whole purpose of practicality.
And all the common ones we care about are fine.
Oh yeah, all the common growth functions. 1 log, n doll, n dollars, $2,000, they're all well-behaved and meet this requirement.
Okay, we have established the rigorous tools, the Turing machine is our model, the worst-case guarantee, and the big O notation that gives us that big-picture growth rate. Now it's time to actually define efficient. We're drawing that line in the sand. Everything on one side is acceptable and fast. Everything on the other is TSP territory, that 120-year disaster.
And that line is defined by polynomial time. known to everyone in the field as Class P. This classification is, I would argue, the most important foundational concept in all of complexity theory.
So what exactly does P include?
P is formally defined as the union of all DTAMEC classes for every possible natural number of the dealer. So if the runtime of a decision problem can be bounded by 1-3 which means linear time, quadratic time, cubic time, or any time complexity where the exponent on all is a constant, that problem falls into P.
So dollars and even something like opening are all included in P. We often refer to these as tractable problems.
Correct. And this applies to massive areas of computation. Think about parsing computer languages. Context-free languages, which govern how programming compilers or natural language parsers work, are decidable using an algorithm called the CYK algorithm.
And how fast is that?
It runs in 1-3 cubic time. Since 3-3-3 holds a polynomial, CFLs are securely within Class P. This ensures that the critical task of understanding sentence structure is efficient.
Now here's where I have to play the skeptic, because this is the common critique I always hear. You're telling me that an algorithm that runs in 1-1-ta is still considered efficient because it's in P. If I run an unbettel algorithm on an input of size, say 100, the runtime is astronomical. It's far worse than many exponential algorithms on small inputs. Isn't this mathematical definition practically useless?
That is a fundamental and absolutely valid challenge to the definition. If an algorithm genuinely ran in 1-1 it would be practically useless for almost all applications, even on moderate inputs, no question.
So why do we, as computer scientists, draw the line there? Why on earth do we include un-1-taler?
Because the definition of P is justified by a strong theoretical insight and, frankly, overwhelming empirical evidence from decades of algorithm design. The line isn't drawn based on an arbitrary number of years. It's drawn based on the structure of the solution.
Okay, explain that structural difference.
The essential complexity gap is between polynomial growth and exponential growth. When a computer scientist finds any polynomial solution, even one with a ridiculously high exponent like 100, it means they have successfully moved away from the try-everything, brute-force, exhaustive search approach.
The thing that defined TSP.
The hallmark of exponential problems like TSP. It means they found a deep structural shortcut within the problem itself.
So the discovery of an algorithm is a key theoretical breakthrough, signaling that the problem is fundamentally tractable.
Precisely. And what we see in practice, time and time again, is that once that initial structural insight is achieved, subsequent work almost always focuses on optimization. People find ways to exploit that structure more efficiently, and they usually manage to pull that exponent down dramatically, often to something reasonable like 2n to 2 or 3 anyway.
So P represents the realm of problems where structural tractability is even possible. The real defining paradigm shift is that leap from exponential to polynomial.
That's the chasm.
So conversely, what defines the class of problems that are generally considered permanently intractable? The realm of inefficiency.
That would be the class EXP for exponential time. This class captures problems that require runtimes bounded by an exponential function. It's defined as the union of all DTIM2 and C. This includes $2, which is bad, $2, which is far, far worse, and so on.
So our goal, whether we're building a compiler or a navigation system, is always to prove that our problem has membership in P, because that ensures the solution scales up efficiently as the input size dollar increases. The vast difference between 2 and 2 and 2 thalers is what separates a solvable problem from a 120-year wait. This brings us to a huge, critical question about the universality of this whole definition. We've based the entire definition of P, our gold standard of efficiency, on this archaic, slow, single-tape Turing machine. I'm sitting here with a modern laptop with parallel processing, billions of operations per second, vast memory, sophisticated caching. Why should I care if the TM solves something in the $3? Doesn't the very definition of P change when I switch to better hardware?
And this is where we rely on the robustness provided by the extended Church-Turing thesis, or the ECTT. It is the theoretical bridge that makes all of complexity theory applicable to the real world.
Okay, what is the core practical claim of the ECTT?
The ECTT asserts that any physically realizable model of computation, your modern multi-core PC, a cellular automaton, a register machine, whatever technology you might build tomorrow, can be simulated by a standard deterministic Turing machine with, at most, polynomial overhead.
Let's break down polynomial overhead. What does that mean? If my laptop solves a problem entire, are you guaranteeing that the theoretical TM can solve it in, say, $1 or
Yeah.
6?
Exactly that. The TM might need to spend a lot more steps to simulate the parallel operations or the random access memory of your PC, but the increase in time is always bounded by some polynomial factor. You might introduce, say, $2 steps of overhead to simulate a single high-level step, but since the simulation time function is itself a polynomial, the resulting overall complexity remains polynomial.
So this is our free pass.
It's our free pass.
The classification of whether a problem is easy in P or hard not in P is an inherent structural property of the problem itself, regardless of the physical machine we use to execute it.
Precisely. We can analyze the complexity of Python code and confidently classify the underlying problem without ever having to sit down and simulate a clunky TM step by step. The ECTT ensures that our line in the sand, class P, is universal and stable, at least for classical computation.
But the analysis is incredibly sensitive to how we define the input size. We have to address the caution when dealing with arithmetic problems.
This is a critical trap for learners. Nuthers is defined as the length of the input in bits, not more a dollar, the value of the number being processed. A huge number, the $, can take a relatively small number of bits to encode. It takes $, and a bits. If we analyze complexity based on the value $, we can make massive, massive errors.
Give us the classic example of addition versus multiplication.
Okay, consider adding two very large numbers, $6 and $9. If that is the bit length of those numbers, the standard school book addition algorithm takes time that is linear in that bit length. It's $. It's extremely fast.
You just go column by column.
You go column by column. Now consider multiplication. Using the standard techniques, multiplication takes time that's quadratic in the bit length because for every bit of 6 card, you essentially have to multiply it against every bit of dollars.
So if we were sloppy and analyzed complexity based on the number value $, we might look at 6 plus y and say that's one operation, that's over $, which would be completely wrong. We have to analyze the cost of manipulating the individual bits on the TM tape.
We must. The moment we start calculating based on the magnitude of $, instead of the length $, we are almost certainly misclassifying the problem's complexity, potentially claiming an exponential time problem is constant time. Always use the size of the required input encoding.
So the ECTT guarantees the stability of P for all classical computation, but you hinted at the one major instability on the horizon.
Quantum mechanics.
Right.
The stability of the ECTT rests entirely on the principles of classical physics. Quantum computers introduce computational primitives like superposition and entanglement that may fundamentally violate that polynomial simulation assumption.
Specifically, Shor's algorithm for integer factoring is the most famous example. Factoring is believed to be outside of P on any classical TM.
But it appears to be solvable efficiently on a theoretical quantum computer. If quantum computers ever realize their full theoretical potential, they would demonstrate a class of computations that a classical TM cannot simulate polynomially.
Which would break the ECTT.
It would force a major reevaluation of the ECTT and potentially redefine what we consider efficiently solvable in the deepest sense. But for all computation based on classical physics, the ECTT holds, and P is stable.
Let's transition now from these abstract definitions to concrete efficiency. We need to see P in action. Let's look at a foundational graph problem. Path. Given a graph, a network of nodes and connections, is node reachable from node super?
This is the problem that underpins everything from Google Maps to network routing to checking data dependencies in a spreadsheet. And fortunately for the modern world, path is firmly and efficiently in P.
How do we solve it?
We solve it using classic algorithms like breadth first search or BFS.
Walk us through the basic structural insight of BFS. Why is it so fast? What's the trick?
The trick is that BFS systematically explores the graph layer by layer, starting from the source node, color dollars. It's an iterative marking process. We mark a Zeller first. In step 1, we look at all the immediate neighbors of Zellers and we mark them. In step 2, we look at all the neighbors of those newly marked nodes and so on.
And you continue this wave expanding outward until you either hit your target, $2, or you just run out of new nodes to check.
Exactly. The genius here is that we prevent repetition. We are very careful to never check the same node or the same path segment twice.
And that's the key structural optimization that prevents an exponential blowup from trying all the possible paths.
That's it. In the worst case analysis, the algorithm has to visit every single node, which we denote as $, the number of vertices, and traverse every single edge exactly one time to confirm reachability or non-reachability.
So the total runtime complexity is something like Leo V plus E.
Correct. And since the input size, $, for a graph, is just the length required to write down all the nodes and edges, $, is proportional to Veller lever plus E doll.
So the runtime is linear in the input size.
It's linear.
Yeah.
And since linear time is a polynomial time, it's $1. We have formally proven the path is in P.
Okay, so that proves membership by building and analyzing a specific algorithm. But complexity theory gives us a powerful shortcut, something that lets us skip that tedious step-by-step analysis for every single new problem we encounter.
That powerful tool is the polynomial time reduction. This is how we build the entire structure of complexity classes without constantly having to reinvent the wheel for every problem.
We've used reductions before back when we talked about decidability, but now we have to make them efficient. What's the new, stricter rule for a polynomial time reduction, which we denote as Adello lep bi?
We enforce two constraints on the reduction function, let's call it 5, that converts an input for problem A into an input for problem B. First, and this is the same as before, 5 must be correct. An input dollars is an instance of problem A if and only if its transformation, f to $, is an instance of problem B.
It has to preserve the yes and no answer.
It has to preserve the meaning. But the second constraint is the crucial one for complexity.
And that is?
The function 5 itself must be computable in polynomial time. If the reduction process itself takes $u time, we've gained nothing. The whole benefit of using the reduction relies on the transformation, Feidler's being fast.
Why is that restriction so powerful? Because it leads us to this fundamental principle that keeps the class P so neat and tidy, what the source calls the free lunch theorem.
Theorem 2.8. It states that if a problem dollars is polynomially reducible to a problem bialas's fifth, all the dollar is in P, then problem dollar is automatically also in P. The classification transfers efficiently.
Let's make sure the proof for this composition is crystal clear for everyone listening. If we combine two steps, and both of them are polynomial, why does the total time absolutely guarantee a polynomial result?
We need to track the time resources in two distinct phases. Phase 1 is the reduction itself, running the function $5. Let's say $5 takes some polynomial time, we'll call it colon, where dollars is the length of our original input, a colons.
Okay.
This reduction produces the new input. Let's call its length $1. Now, because $5 runs in polynomial time, the length of its output, colon, is also bounded by a polynomial in Hans. Specifically, dollar can't be longer than declama's dollar. A Turing machine can't write an output that's longer than the number of steps it took to run.
Right. So phase 2 is solving problem B. We already have an algorithm for B that's in P, which takes time, PM, where $, is another polynomial, and $, is its input length.
So the total time to solve our original problem, A, is roughly the time for the reduction plus the time for the B algorithm running on the result. So total is about clon plus PM.
And since we know $, is no bigger than umang,
The total time is bounded by the composition of the two functions.
and we're composing two polynomials. Let's use some concrete exponents to make it real. Say the reduction Q is quadratic, so OM2, and the existing algorithm Q is cubic $.
Then the total time for the whole process is $3, which simplifies mathematically to $6. The essential, beautiful property of polynomials is that if you compose two of them, the result is always another polynomial.
And that closure property is what makes class P the robust, stable structure we need. If we allowed an exponential reduction, composing it with a polynomial algorithm would instantly yield an exponential runtime, and the whole classification system would just crumble. Now that we have the ultimate tool, the polynomial reduction, let's survey the landscape and look at some of the key residents of class P. These are the problems that form the foundation of our efficient computational world.
P is vast. It's our comfort zone. And knowing what problems are already known to be in P allows us to focus our development effort on optimization, not on a fundamental, desperate search for a solution.
Let's start with an example that's directly related to the path problem. EMPT NFA DOL. This is the emptiness problem for non-deterministic finite automata. Given an NFA, does it accept any words at all? Is its language empty?
This is a critical theoretical problem for language theory and compiler design, but we don't have to invent a brand new algorithm from scratch to solve it. We can just reduce it to graph reachability.
How does that work?
We just map the NFA states and transitions directly onto a graph. The states become nodes, the transitions become edges. The NMPT NFA question then becomes a simple graph question. Is there a path from the NFA's start state to any of its designated final states?
Wait, if there's a path, that means it accepts a word, so the language is not empty. So we're actually reducing NMPT NFA to the complement of path, or overline path.
Exactly. We already proved path is in P because it runs in linear time. And since the complement of an efficiently solvable problem is also efficiently solvable, you just run the path algorithm and flip the final yes/no answer. Overline path is also in P.
And since the reduction itself, just creating the graph from the NFA, is super fast and polynomial.
Theorem 2.8 guarantees that EMPTNFA is also efficiently solvable and therefore a secure resident of P.
That's a beautiful demonstration of the efficiency shortcut. What about the problems that handle the structure of communication, like our context-free languages?
As we mentioned earlier, every single context-free language is firmly in P. The standard algorithm that determines if a given input string belongs to a CFL, a critical task in programming and linguistics, is the CYK algorithm. The worst-case runtime for CYK is $3.
Cubic time is perfectly acceptable. It means parsing and structural analysis scales appropriately, allowing our compilers to work on programs of any reasonable size without taking years and years.
And finally, let's look at a foundational problem in some really high-stakes areas like banking and security. Curl primals. Given two very, very large numbers, 6 and dollars, are they relatively prime? In other words, is their greatest common divisor equal to 1?
The efficiency of this problem is absolutely non-negotiable for modern cryptography, specifically protocols like RSA. If checking for relative primality were hard, we would have no secure public key infrastructure.
Fortunately, this is solved by the ancient Euclidean algorithm. And when we analyze its complexity based on the size of the input bits, none dollar, the Euclidean algorithm is incredibly efficient. Its runtime is linear in the bit length.
Linear time is essentially as fast as you can possibly get because, as we established earlier, you have to spend at least $9 just to read the input in the first place.
Right. The ability to check for relative primality in linear time is what makes massive, secure key exchanges feasible thousands of times per second all over the globe. The fact that the Euclidean algorithm is so fast ensures that RelPrum is securely in P, and that underpins our entire digital economy. All these examples, from graph reachability to cryptographic primitives, really show the breadth of vital problems that are efficiently solvable.
So, as a learner, the main takeaway from this entire deep dive should be knowing the two robust ways that you can prove a new problem is in P.
The first way, and sometimes it's necessary, is the direct approach. Specify a concrete deterministic algorithm. Then, conduct the rigorous worst-case analysis using the Teller notation and demonstrate that the time is bounded by 1 as in G for some fixed constant Tiller. That is the primary form of evidence.
And the second, more elegant and common method in complexity theory.
That's the method of leveraging the closure properties of P. You show a polynomial time reduction from your new problem to a problem that you already know resides in P. Because P is closed under this polynomial time composition, you can chain P algorithms together, and the total time remains polynomial. That classification automatically transfers. It allows you to classify incredibly complex problems based on existing knowledge.
We've reached the end of this deep dive into computational efficiency. Our mission was to elevate the discussion from is it solvable to is it practically feasible, and we've defined that standard robustly as class P polynomial time.
The core lesson here is understanding that line between the possible and the practical. P is our working definition of practical. If a problem is in P, we are justified in focusing our resources on optimization, on trying to reduce that constant factor or lower the exponent.
And if a problem is believed to be beyond P's, like the TSP,
Then we have to abandon the search for an exact, worst-case efficient algorithm. We have to shift our focus to approximations, heuristics, or randomization.
and that stable definition of P, we noted, rests entirely on the extended Church-Turing thesis. That's our theoretical guarantee that the difficulty of a problem is independent of whether we're using an antique TM or the fastest supercomputer in the world.
And that stability, that very foundation, leads us to our final provocative thought for you to mull over.
We rely on the ECTT to ensure the universality of P. But the very existence of theoretical quantum computers challenges the ECTT. It suggests that the most powerful, physically realizable machine might be able to solve a class of problems that are fundamentally non-polynomial for every classical machine we could ever build.
So the question is this. If the ECT fails universally, if quantum computation introduces a genuinely new level of efficiency that cannot be simulated polynomially by a classical Turing machine, then the entire framework of what we classify as efficiently solvable has to shift. Are problems like factoring only hard relative to our current understanding of classical physics, or are they truly fundamentally hard in the universe of all possible computation?
That fundamental question about the physical limits of computation is the exciting complexity challenge that future engineers and computer scientists will inevitably have to face.
Something to ponder while you enjoy the linear time solution that quickly got you the path home. Thanks for diving deep with us.
We'll see you next time.